Good evening. 1 o'clock, 7:30, but we will wait a couple minutes for people to join in. We will start no later than 7:35. Thank you. This is SK Ghosh. I would like to welcome each and every one of you to this continuation of our training and capacity building program under component S9 of urban resilience. We started on these seminars in mid-March to the middle of July. So we have about a month left of these seminars. Is on seismic detailing of special and intermediate moment frames of concrete. Tomorrow we will do a companion seminars in many ways on the seismic detailing of special reinforced concrete shear walls. This is a picture of the reinforced cage of a special moment frame in California, which is seismic, as you know. So this is what special detailing look like. Special moment frame means specially detailed moment frame. There are 3 levels of detailing in our codes and standards: ordinary, intermediate, and special. This is what special detailing looks like. Very close spacing of the transverse reinforcement is the main thing that stands out. And there are
It's still lagging. I mean,
and there are all kinds of other details about the hooks and things that I will go into as the seminar progresses. So today's seminar, we have a brief introduction, which we are basically going through. Then material qualification, what are the restrictions on material strength and so forth. Then detailing of special moment frame beams and intermediate moment frame beams. Similarly, columns of special moment frames and columns of intermediate moment frames. Then joints of special moment frames and intermediate moment frames. The detailing that we will discuss will BNBC 2020, which became official pretty recently. It was gazetted on February the 11th of 2021. So this is our base document, and the detailing requirements of that document are based on the 2008 edition of ACI 318 Building Code Requirements for Structural Concrete. ACI is American Concrete Institute. This standard is adopted by the International Building Code and used throughout the many places abroad. So ACI 31808 provides the basis for the seismic detailing requirements of BNBC 2020. I did want to point out, I think this is kind of that beyond ACI 31808, first of all, is the basis of the requirements of BNBC 2020, because BNBC 2020 was started in 2008 and was essentially completed in 2010. So ACI 31808 was then the latest edition of ACI 318 Since then, ACI has published ACI 318.11, 318.14, and ACI 318.19. So 3 full editions have been issued after the 318.08 edition, and in 2021 IBC, which is the latest one, the reference standard is ACI 318.19. There are significant changes from one edition to the, meaning that the detailing requirements I will share with you today have evolved some. If you look at the latest ACI 318, you will see that some details are different. By no means all, but some of them have changed. We detail by Chapter 21 of ACI 318.08. That is the seismic detailing requirements chapter, if you want to be more specific. We have to comply with the rest of ACI 318 as well. The rest of ACI 318 does not go away. 21 chapter. The rest of ACI remains applicable unless modified by Chapter 21. There are instances a provision in the main body of the code would be modified in Chapter 21, very probably for high seismic use, design categories D, E, and F. So in those cases, obviously the modified requirement applies, but if that is not the provision in the front part. Okay, sorry about the interruption. There were apparently my voice was breaking out. I hope we fixed it. You have to be the judge. Is it better now?
Yeah, there's a delay, but let's keep up and let's continue with that.
Okay, so the discussion that we were on when we design or detail by Chapter 21 of ACI 318.08, the remainder of ACI 318.08 doesn't become inapplicable. All of it remains applicable unless modified in Chapter 21. BNBC 2020, the provisions that concern us are in Part 6, Structural Design. Chapter 8 is Detailed in Concrete Structures. And in that chapter, Section 8.3 is Earthquake-Resistant Design Provision. That's where you will find the requirements that we will discuss today. And just like when you design by Chapter 21, the rest of 318 applicable. When we are detailing by Section 8.3, Chapter 6, Strength Design of So Part 2, Chapter 6, Strength Design of Reinforced Concrete Structure remains applicable except where modified by Chapter 8. Okay, so keep that in mind. Chapter 6 still remains applicable unless modified by Chapter 8. In this slide set, all section numbers that are not in blue are from 3. All section numbers that are in blue are BNBC 2020 Part 6, Chapter 8 or Chapter 6 section numbers, unless otherwise noted. One or two places it may be different.
You're still, yeah. Can we restart WebEx or maybe restart your computer?
Sorry, there is apparently more problems, so we'll take a little time. Okay, sorry about the long delay. Hopefully it will work now, but I don't know. Is it better?
Mm-hmm.
So I think this is the slide we were on. The black are ACI 31808 section numbers, blue are BNBC 2020 section numbers out of part 6, chapter 8 or chapter 6. This slide, we just try to tell you that precast concrete moment frames, which are definitely included in chapter 21 of ACI 31808, are not mentioned in BNBC 2020 part 6 chapter 8. Okay. So in ACI 318, special moment frames of precast concrete are outside the scope of this presentation. The ACI 31808 edition has provisions for special moment concrete. I did not include them in the slide set because BNBC doesn't have it. Intermediate moment frames of precast concrete are simply not recognized by 318. And when it comes to ordinary moment frames, there is no difference between precast and cast in place. The same provisions apply. Now, if you like, in many ways, the basis of the detailing requirements that we have in 31808 and BNBC 2020. What you see here is the idealized force displacement of a particular structure subjected to the design earthquake of BNBC 2020 or ASCE 7. The design earthquake that we talked about in an earlier seminar, 2/3 of the maximum considered earthquake. On the x-axis are the lateral displacements suffered by the structure in the process of going through the earthquake. And on the y-axis are the forces induced in the structure as it goes through the earthquake. Okay. So the maximum force that the structure is induced in the structure is F sub U, and the maximum displacement suffered by the structure is capital delta sub U. If I now turn around and say that we are required to design this structure for elastic response to this particular earthquake, the design earthquake of the code, the immediate conclusion would be that we must provide the structure with a strength level at least equal to F sub U. If we decide that we can afford that highest strength level, that all we can afford is a much lower strength level F sub E, then if the design earthquake comes and hits our structure, when the earthquake-induced forces equal and then exceed F sub E, the structure will start cracking and yielding in places. And that will be the end of elastic behavior. At that point, we are talking about deformations that are not going to be recovered, okay? So that are associated with damage. The inelastic displacements will not follow the flat top as presented in the picture because this is an idealized picture. But the main point is that as long as behavior remains elastic, the earthquake passes, you get the structure back intact. There is no residual, there is no damage. When we supply a strength level F sub E lower than F sub U at one point, structural behavior is not elastic anymore. The structure starts cracking and yielding in places. That is the beginning of inelastic displacements that will be residual, that will not be recovered. Is damage associated with it. Okay. Many observations and analytical studies have established that the total displacement delta sub U is about the same, not exactly the same as in this idealized picture, but about the same, irrespective of whether... Can you hear me?
Yeah.
Yes, we can hear you.
Sorry, I have no idea what is happening today, and it's kind of difficult to do a seminar this way with multiple interruptions and loss of time. But anyway, thank you for your patience. Hopefully the rest of the way will go without a hitch. Let's hope so anyway. Okay, so the total displacement is the same irrespective of whether structural response to the earthquake is elastic or inelastic to various degrees. In seismic design by the code, we do not design to keep our structure elastic under the design earthquake, because that would be expensive and that is totally unnecessary. We allow code use design for a much lower strength level than would be required for elastic response to the design earthquake. So we do allow a certain amount of inelastic displacement under the design earthquake that would be associated with damage. We would like the damage to be repairable, but we allow damage. However, the extent of the inelastic deformation should not be such that the structure collapses on us. So the inelastic deformation has to be within the inelastic deformability of the structure, which is, as I said, the ability of the structure to deform laterally beyond the stage of elastic response while still sustaining full factored gravity loads. Inelastic deformation capacity comes from proper detailing of the members and the joints. So seismic design, first of all, is an exercise in trade-off between strength and deformability. The higher the strength, the less the need for inelastic deformability, and the lower the strength, the higher the need for inelastic deformability. Secondly, inelastic deformability comes from proper detailing of the structural members and joints. The bridge, so seismic design is a two-part affair. We have to design for the strength that our code tells us to design for, and we have to detail by the rules that go together with the strength level that we have selected. The bridge between the two, the strength level and the detailing requirements, is the R value that is in the denominator of the design base shear. The higher the R, the lower the design base shear, the higher the need for fancy detailing that will give us high inelastic capacity. Okay. The lower the R, the higher the strength level, the lower the need for fancy detailing that would give us high inelastic deformation capacity. So that is very basic. The provisions of Chapter 21 of ACI 318 relate detailing requirements to type of structural framing, whether it's frame or shear wall or whatever, and seismic design category, which we have discussed. Seismic design categories are adopted directly from ASCE 7 and relate to considerations of seismic hazard level, which is associated with the seismic zones that you have in BNBC 2020, soil type, occupancy, and use. I have taken this page from BNBC 2020. This tells you the same story in slightly different language. So 831 of BNBC 2020 tells you this section contains special requirements for design and construction of reinforced concrete members of a structure for which the design forces related to earthquake motions have been determined on the basis of energy dissipation in the nonlinear range of response. That is the key thing. So we are not doing design for elastic response to the design earthquake. We are allowing inelastic behavior under the design earthquake, which would be associated with damage. The R values that we talked about, sorry, this is another problem. Anyway, so the earthquake resisting structural systems I discussed with you on an earlier occasion: moment resisting frame system, bearing wall system, dual system, and building frame system. Okay. Now, moment resisting frame system obviously has moment frames in them. The bearing wall system does not. Dual system has moment frames in them, and the building frame system has moment frames, but they are not part of the seismic force resisting system. So in this part of what is table 12.2-1 of ASCE 7 and table 6.2.19 of BNBC 2020, we have reproduced the rows that include moment frames of concrete. Okay. So moment frames of concrete are used in moment resisting frame systems or in dual systems. There are two types of dual systems recognized in ASCE 7. Dual systems that feature special moment frames of concrete, and dual systems that feature intermediate moment frames of concrete. Now, if we look at moment resisting frame system, you see special reinforced concrete moment frames are assigned an R value of 8, which would be a very low design force level. Intermediate moment frames R is 5, so that is considerably higher design force level. Ordinary moment frames are of 3, which is the highest design force level of any moment frame of concrete. Okay. So this table, as discussed earlier, also has doses of D and the height limits that we will not go into today. In Bangladesh, as mentioned earlier many times, you do not have design categories E and F, so your table ends here. Okay. The height limits in ASCE 7 are in feet. Here I have converted them into meters. In BNBC table, you have the height limits in meters. Okay, we now go into the restrictions on materials. Concrete, remember, we are, I said this not too long ago, but with technical difficulties, I think it is better to repeat that we are talking about detailing by chapter 21 of ACI 318, which is seismic detailing. And we, in chapter 21 of ACI 318-08, most of it is special detailing that is needed for seismic design category D. One section is on intermediate detailing, which is required for seismic design category C. The ordinary detailing is in the main body of ACI 318. Okay. So when we talk about restrictions here, we are talking about restrictions in moderate or high seismic applications, design categories C, D, E, or F. Okay. Or I should say just C and D. Now, some of the time, some restrictions apply only in D, other restrictions apply also to C and D. You have to look at the provision of the code to see which way it is. At the beginning of chapter 21, ACI 318 tells you where these material restrictions apply, and I can tell you that they are only for special moment frames. Okay, so keep that in mind. Compressive strength of concrete cannot be any less than 3,000 psi. I convert it to but I don't have any feel for metrics, so I will probably say the American unit numbers, and the SI numbers are on the slide. So compressive strength not less than 3,000 psi. In the US at least, lower strength concrete has now become difficult to find, so the less than 3,000 psi is not much of a restriction. I do not know about Bangladesh. Obviously, maybe that it is a real restriction. The important thing is that we have no upper limit on the strength of normal weight concrete that can be used in applications, including high seismic applications. ACI 318 is one of the few codes left in the world that has no restriction, no upper bound on the strength of concrete that can be used. We have made adjustment for the different properties of high strength concrete, but it is never disallowed. Lightweight concrete, on the other hand, cannot be more than 5,000 psi in strength for high seismic applications. So higher strength cannot be used in special moment frames and special shear walls. That's have test results available on structural members or sub-assemblages using higher strength concrete. As such results become available, this limit may be relaxed. At one time it was 4,000 psi, now it is 5,000 psi, the upper limit. Reinforcement, the preferable reinforcement is A706, which comes only in grade 420 or grade 60, as we call it, 60,000 psi yield strength. That we commonly refer to as weldable steel, but that is the preferred type, not because it is weldable, but because the properties are very tightly controlled. Alternatively, ACI 318 allows us to use normal billet steel A615, grade 40 and 60, however, with supplementary requirements that we will look at. In BNBC 2020, it is Bangladesh standard ISO 6935-2, grades 300, 350, 400, 420. Those are steels sold in Bangladesh that I am not particularly familiar with. Those are allowed. Or ASTM grade A615 grades 275 and 420, which is the same as 31808 with supplementary requirements. So BNBC is the same as ACI 31808, except that those Bangladesh standard steels grades 300, 350, 400 and 420 are allowed. So the supplementary requirements that we talked about. So A615 steel has to satisfy the supplementary requirements to be used in special moment frames or special shear walls. The actual yield strength based on mill tests does not exceed F sub y, the specified yield strength, by more than 18,000 psi, 18 ksi. Retests can take you another 3 ksi, but no more than that. That retest requirement was in ACI 31805, in ACI 31808. It's not there. This is why I put it in blue. It is a BNBC requirement, not a requirement of 31808. Anyway, this is a very, very significant requirement. This is the first time I will say this, and I may repeat it many times. In seismic design, more is not necessarily better. If you specify grade 60 steel, somebody cannot substitute that with grade 75 steel. That's not a good thing to do. more is not better. That is because if the yield strength of the reinforcement is higher than you specified, the flexural member reinforced that with that steel will have higher flexural strength than you counted on, and this member with higher flexural strength will attract more shear forces to itself in an actual earthquake situation. We will not be correspondingly increasing the shear strength, brittle shear failure more likely. So higher strength reinforcement than specified is a problem. So we are putting a limit on it. The actual yield strength cannot be any more than the specified yield strength by more than 18,000 psi. Okay. Now, there is another requirement that we will look at on the next page. And then there is a requirement in BNBC that we didn't have in SCI 31808 that we since have added in 314. This second requirement makes the elongations of A615 steel the same as the elongations of A706 reinforcement. So minimum elongation over an 8-inch gauge length shall be 14% for bar diameter 10 millimeters to 20 millimeters, at least 12%, etc. So whatever the elongations are for A706 steel are being required for A615. The final, so I talked about the actual yield strength shall not be higher than specified by more than 18,000 psi. I talked about the elongations being the same. Final requirement is that the actual tensile strength shall be no less than 125% of the actual yield strength. That is in order for the reinforcing steel to have inelastic deformation capacity, which will then translate into inelastic deformation capacity of the member reinforced with that steel. So no less than 1.25. This requirement has kept a lot of foreign steel out of the US market. I know that many foreign reinforcing bars cannot meet this requirement of actual tensile strength to specified yield strength of no less than 1.25. I do not know the situation in Bangladesh, but this is a requirement. In the US today, for high strength reinforcement, particularly in SCI 31819, the 1.25 requirement has been relaxed, but I need not go into that today. In ACI 318, these stressed members within limitations are allowed to be part of the seismic force resisting system, but there is no mention of those in BNBC 2020, so I will skip this 318 requirement. It just says the pre-stressing steel shall comply with relevant standards. The value of sub YT, that's yield strength of transverse reinforcement, used to compute the amount of confinement reinforcement, shall not exceed 700 MPa, that is 100 KSI. Okay, so we are allowing transverse reinforcement with yield strength of up to 100 KSI for confining longitudinal reinforcement in concrete members in high seismic applications. This has major connotations, as I'll show you in a second. Okay, so up to 100 KSI transverse reinforcement is being allowed. Having said that, the value of F sub Y or F sub YT, F sub Y is for longitudinal reinforcement, F sub YT is transverse reinforcement, used in design of shear reinforcement shall form 11.42. If you go to 11.42, it says it cannot be more than 60 KSI in yield strength. So for confinement, we are allowed up to 100 KSI transverse reinforcement, but for shear, for use as, for transverse reinforcement used as shear reinforcement, we cannot use F sub y in excess of 60 KSI. The second restriction applies because if we use high strength reinforcement, if we allow somebody to use F sub y much more than 60 KSI in shear computations, there will be very likely major shear cracks, which we do not want in our concrete members. Okay? The shear reinforcement will yield, the shear cracks will get wide, and that can cause significant problems. So for confinement purposes, high strength transverse reinforcement is fine, but for shear, high strength, the high yield strength of the transverse reinforcement cannot be used in computation. In computation, you have to use something no more than 60 KSI. Now, why is 100 KSI transverse reinforcement as important as I am telling you? Okay, the reason is here. What I'm showing you are detailing requirements for columns of special moment frames. These are detailing requirements for columns, and very importantly, columns of special moment frames. Okay. For columns of special moment frames, we consider regions of potential plastic hinging at each end. The length of the region is the smallest stop. Okay. The larger plan dimension, 1/6 of the clear span, 450 millimeters. Okay, so once again, the larger plan dimension, 1/6 of the clear span, 450 millimeter, whichever of the three is the smallest, is smallest or largest. 1 second. This I believe, I will check. We don't have any break, but I will check. I think this is a mistake. I think this is the largest of the three, as I recall. Anyway, I'll check on that. We have this, and you can check on that in BNBC very easily. We have the region of potential plastic hinging, within which we have to have closely spaced transverse reinforcement. The spacing shall not exceed 1/4 of the minimum plan dimension, 6 times the longitudinal bar diameter, or S sub x. Okay, and this S sub x I will explain in just a little bit. Outside of the region of potential plastic hinging, the spacing cannot exceed 6 times the longitudinal bar diameter, or 6 inches, whichever is the smaller of the two. Okay. So the detailing of special moment frame columns will come a little bit later in the presentation, so I will talk about it at that time. What I want to discuss now is within the region of potential plastic hinging, the transverse reinforcement, in addition to meeting the minimum spacing requirement, must also meet a minimum cross-sectional area requirement. So there is a maximum spacing requirement that you cannot violate, but there is a minimum cross-sectional area requirement. The total cross-sectional area of the three legs in this particular case, in each direction, cannot be any less than the larger value given by those two equations. Okay? So the minimum cross-sectional area of transverse reinforcement separately in two orthogonal directions cannot be any less than the larger value given by two different expressions. If you look at the expressions, you have F sub C prime in the, well, first of all, let me say that these requirements, minimum cross-sectional area requirements, are so onerous that they control over the very stringent maximum spacing limitations. From here, you will typically get for a California frame, let us say 4-inch maximum spacing, but the cross-sectional area requirement is so high that for a number 4 or number 5 transverse reinforcement, our number 4 is half-inch, that would be 12 or 13 millimeters. For transverse reinforcement of that size, you will end up with spacing of 2.5 or 3 inches, okay, which is very tight when you consider concrete placement. So, and you notice that we have F sub C prime in the numerator. So we go from 4,000 to 6,000 to 8,000 to 10,000 PSI concrete. The minimum cross-sectional area requirement of the transverse reinforcement increases. And pretty soon for 10,000 PSI concrete, we are looking at 1 or 1.5 inch spacing of transverse reinforcement, which is impractical. We cannot place concrete with that kind of spacing. So having said that, there is no upper limit on the strength of concrete that we can use in special moment frames. This is a de facto hidden limit. The only way out of this is high strength transverse reinforcement. If as F sub C prime goes up, we are able to increase F sub YT with this 100 KSI transverse reinforcement, then we will still be able to provide the required confinement at a reasonable spacing. So that is the big attraction of this permission of using up to 100 KSI transverse reinforcement for confinement. Now, this is a graphic picture of what I'm talking about. So a friend of mine in Seattle gave me this picture, Kerry Kopczynski. You look at the cage that he ended up with, the column cage with 60 KSI reinforcement, 420 MPa. And this is the cage with, I don't remember now, he didn't have 100, he had 75 or 80. Anyway, this is higher strength reinforcement. And you see what a difference it makes, how much more reasonable the spacing becomes when you have high strength transverse reinforcement available. Now, when we talk about the transverse reinforcement or the longitudinal reinforcement being confined, this is what confinement looks like. It is not one tie all around. The specific requirements are every other bar shall be supported by the corner of a tie or a cross tie. Every other bar shall be laterally supported by the corner of a tie or a cross tie. The maximum spacing center to center between any two supported bars, 14 inches. The clear spacing between a supported bar and an unsupported bar, this clear spacing is no more than 6 inches. Okay, so the maximum spacing between any two supported bars, 14 inches. The maximum clear spacing between a supported bar and an unsupported bar, 6 inches. And then the tie that goes all around has to be closed by seismic hooks. The cross ties, as we call them, has one seismic hook at one end, one standard seismic hook is a 135-degree hook with 6 bar diameter extension beyond the bend. The 6 diameter has a minimum of 3 inches on it. And you see that on alternate cross ties. So on this one, the seismic hook is on this face. On the other one, the next one, the standard hook is on this face. We have to alternate. And then on the next tie, next set, whatever, next transverse reinforcement ensemble, if you come out of the screen, on the next cross tie, out of the screen, on the next the transverse reinforcement, This angle would be 90, that angle would be 135. All of this is actually practiced. This is special detailing that the contractors have to get used to. Okay. Welding of stirrups, ties, inserts, other similar elements to longitudinal reinforcement that is required by design shall not be permitted. This is a very serious requirement of the code. BNBC in a way spells it out a little more. So reinforcement required by factor load combinations, which include earthquake effect, shall not be welded except as specified in section such and such. So BNBC tells you that the that welding is permitted when you are splicing longitudinal reinforcement, but otherwise the welding of longitudinal reinforcement to transverse reinforcement is not permitted. The ACI language is straightforward. Welding of stirrups, ties, inserts, or other similar elements to longitudinal reinforcement that is required by design shall not be permitted. Okay, if you must weld a tie to a longitudinal bar, it has to be to a construction bar added for that purpose. It cannot be a bar that carries stresses by your design calculation. Okay, we come to detailing requirements for beams initially of special moment frames, beams of special moment frames. What is a beam? What is a column? In non-seismic design does not make much of a difference. You decide, and anyway, in seismic detailing, it makes a difference because column detailing is much more stringent than that of beam detailing. The arbitrary dividing line that ACI 318 has drawn is an axial force level of A sub G F sub C prime over 10, 1/10 the gross cross-sectional area times the specified compressive strength of concrete. Okay. If factored axial compression is less than or equal to that, the member is a beam. If the factored axial compression is larger than that, the member is a column. Now, when we say factored axial compression, this is due to gravity as well as earthquake-induced axial forces. Okay, that is very important. So if a member is classified as a beam, the clear span has to be no less than 4 times the effective depth. Clear span larger than or equal to 4 times the effective depth. So a very cannot be part of the seismic force resisting system. It has to be a reasonably slender beam. Then the short to long dimension ratio cannot be any less than 0.3. Okay, so if you have let's say a 30-inch deep beam, the width cannot be any less than 9 inches. The width of a beam has to be no less than is very important. Okay, no less than 10 inches, 250 millimeters. And also there is another restriction that I better explain with a picture. The second restriction talks about a case where a beam framing into the column is much wider than the beam. Now, when that is the situation, a beam framing into a column is wider than the beam, how much of the wide beam can be considered as part of the, can be considered as effective when it comes to the frame acting as a special moment frame? How much of the width of this wide beam can we count on is the question. So in this picture, this is the direction of analysis. Column dimension in the direction of analysis is always C sub 1. Column dimension perpendicular is C sub 2. Okay, if we cut a section here, the section looks like this. This is the column. This is dimension C sub 2. C sub 1 is into the screen. I hope you follow me. Okay, and then this is the wide beam. Now, how much of the wide beam is effective? ACI 318 is saying this overhanging flange width cannot be any greater than the smaller of C sub 2, this column dimension, C sub 2, this C sub 2, and 75% of C sub 1, the perpendicular column dimension, this column dimension. So this overhang cannot be any larger than the smaller of C sub 2 and 75% of C sub 1. The rest of the beam, if the beam is any wider than that, the rest of it has to be discounted. So, so this is an important requirement which keeps, this is extremely important, flat plate column frames where we do not have any column line beams. We have slabs supported directly on columns. Can those slabs act as beams of a special moment frame? And the answer is no, because you cannot meet the detailing requirements that I just showed you. If you take only that much of a flat plate as your beam, you cannot satisfy the detailing requirements of ACI 318. Now, ACI 318 itself never says that flat plate cannot be part of the resisting system, but BNBC spells it out, which I truly appreciate. So this particular section of BNBC that I have cited tells you the provisions for special moment frame shall not permit the use of slab without beam as part of seismic force resisting system. Okay, please keep that in mind. Very important. Flat plate column frames cannot be part of the resisting system in seismic design category D. In seismic design category C, you can do it. Then you need intermediate moment frames, and we have provisions for that I'll share with you. Okay, but special moment frame, no. In design category D, you will still see a lot of special moment frames built, but they are not part of the seismic force resisting system. The seismic force is taken entirely by shear wall cores or brace frames or something like that, without depending at all on the slab column frames. Okay, beams of special moment frames is what we are discussing. The longitudinal reinforcement. Let us look at the requirements. So minimum 2 bars continuous top and bottom. That's the first thing. Secondly, maximum reinforcement ratio top as well as bottom, 2.5%. That is a constructability requirement. There is nothing else to it. There is no science, no other something. So 2.5% is a construction requirement. More than that, it gets congested, and there are other problems. So the minimum reinforcement top as well as bottom, 140 over f sub y or 0.25 square root of f sub c prime over f sub y, whichever is the smaller of the two. Okay. So I'm sorry again. The row, the minimum reinforcement is the larger of the two, 140 over f sub y or 0.25 square root of f sub c prime over f sub y. And in our units at 44 psi, that number takes over. That gives you a larger value than 140 over f sub y. I don't know the metric number. Okay. So 44 psi, the 0.25 square root of f sub c prime over f sub y will give you a larger number than 140 over f sub y. Now, very importantly, you must have at every support section as much negative reinforcement as you must have half as much positive reinforcement as you have negative reinforcement. If you have number 8 bars at the top, our number 8 is 1 inch diameter. If you have number 8 bars at the top, you must have at least 4 number 8 bars at the bottom, 1/2. The positive moment strength has to be no less than 1/2 of the negative moment strength. This is extremely important because earthquakes change direction. Yeah. So when gravity would always cause negative bending moment at the support section of a beam. So if you are doing gravity design, you do not need any bottom reinforcement at the beam section. But earthquakes reverse direction. For one direction of earthquakes would also cause negative bending moment at the same support section, which would add to gravity moments. But for the reverse direction of earthquake, the earthquake will cause positive bending moment, which may exceed the positive bending moment caused by earthquake forces may exceed the negative bending moment caused by gravity, and you may end up with net positive bending moment, which would require bottom reinforcement. Okay? So gravity thinking engineers cannot understand this or appreciate this, and after every earthquake we see bottom cracks at beam supports, which should not be there. Okay? So this is a very important requirement. And then nowhere along the span of the beam can the negative or the positive moment strength be any less than 1/4 of the negative moment strength at 1/4 of the larger negative moment strength at the two support sections. This is a mouthful, so let me explain. Let us say we have 7 number 8 bars at this support section of the beam, 8 number 8 bars at that support section of the beam. Larger of the two is 8 number 8. 1/4 of that is 2 number 8. So we cannot have any less than 2 number 8 bars at the top or the bottom of the beam at any section. So nowhere along the beam span can the negative moment strength or the positive moment strength be any less than 1/4 of the larger negative moment strength supplied at the two support sections. Transverse reinforcement. We consider a region of potential plastic hinging at each end, the length of which is 2 times the total depth of the beam. 2 foot deep beam, 4 feet is the plastic hinge length. Within that, we have to have closely spaced transverse reinforcement. The spacing not to exceed the smallest of those 4, 1/4 of the effective depth, 8 times the smallest longitudinal bar diameter, 20 and 12 inches, okay, 300 millimeters. This is 31808. So, okay. So, outside of the potential plastic hinge region, you can have, now I should very importantly mention that transverse reinforcement in the plastic hinge region has to be in the form of hoops, which is a closed piece of transverse reinforcement. A closed piece of transverse reinforcement that has to be closed by seismic hooks, 135-degree hooks with 6 bar diameter extension, etc. Okay. Now there are 2-part hoops that we will see and talk about. Outside of the potential plastic hinge region, we can have open stirrups at a spacing not to exceed 1/2 of the effective depth. And then where the longitudinal reinforcement is spliced, the splices have to be confined by hoops, again, closed transverse reinforcement at a spacing not to exceed 1/4 of the effective depth, or 100 millimeters, whichever is the smaller of the two. Okay, D by 4 or 4 inches, whichever is the smaller of the two. So maximum spacing no less than any of those 4 quantities. In ACI 31811, I did, most of the time I didn't go to later editions, but this I think is a very important change that happened in 11. The spacing of the hoops in the plastic hinge region was changed to this: 1/4 of the effective depth, 8 times the longest bar, 8 times the smallest longitudinal bar diameter became 6 times the smallest longitudinal. 24 hoop diameter was deleted, and 12 inches became 6 inches. Okay, so we are now looking at tighter spacing of the hoops in the plastic hinge region, starting with 31811, and that change was the result of testing at the University of California, Berkeley. So these are the tests that they did, reversing cycling loads, and they found that the black hysteretic loops are for beam into 31808. The red is for beams detailed by 31811 with the tighter hoop spacing. And you can clearly see that the performance increases, performance improves rather considerably. So that was the basis for the change. Now, so we are still talking about beams of special moment frames and transverse reinforcement specifically, where hoops are required. Primary flexural reinforcing bar closest to the tension and compression forces shall have lateral support, etc., etc. If you read this, the point to the whole thing is that in the region of potential plastic hinging, those hoops are like the column transverse reinforcement. Every other bar shall be laterally supported by the corner of the tie and the cross tie and all of that. Okay, so where hoops are required, primary flexural reinforcing bar closest to the tension and compression forces shall have lateral support conforming to. So if you read this, you will see that this is what it means. You have to confine the plastic of a special moment frame beam the same way as you confine the plastic hinge region of a special moment frame column. The ties and cross ties have to be configured similarly. Okay. Shear design of special moment frame beams, very, very important. So we do not design a special moment frame beam for the shear our analysis says develops in it. We have to design a special moment frame beam for the largest shear that can develop in it. Okay? So the largest shear, to calculate the largest shear that can develop at a special moment frame beam section, let us say this left support section of this beam. Okay, if we want to calculate the maximum shear at the support section, we have to consider the largest bending moment in this direction that can act at that support section. That will be a positive bending moment. We have to consider the largest bending moment that can happen in this direction. This is clockwise, this is also clockwise, this is now a negative bending moment at the opposite support section. We will add the two moments together, divide by the span. That will give us the shear, except that we have to superimpose the shear due to gravity acting on the beam. And when we say gravity, this is not 1.2 dead and 1.6 live. This is the gravity part of the seismic load combination. So this will be 1.2 dead plus 0.5 live, if you catch my drift. This is very, very important. The gravity sitting on this beam is not the gravity that we consider in our gravity load combination, 1.2 dead and 1.6 live. This is the gravity part of the seismic load combination, because we are looking at the special moment frame subject to an earthquake. Okay? So it is the gravity part of the seismic load combination, which would be 1.2 dead plus 0.5 live. So the largest bending moment that can act, we have a name for that. We call it the probable flexural strength. So that brings up the point that in ACI 318, we have three different flexural strengths that are defined. The first is nominal flexural strength. The notation is M sub N. We calculate that with nominal member dimensions. If it is a 10 by 20 beam, in reality it may be 9.5 by 11.75, but we will take it as 10 by 20 nominal. Reinforcement the same way, whatever is intended by design, we will assume is there. And then very importantly, the stress in the reinforcement will be taken equal to the yield strength. So that is nominal strength. In flexural design, we do not count on the entire nominal strength. We discount it by a phi factor, and the phi times M sub N is called the design strength. We have never called it M sub D or anything like that. Design moment strength is always phi times M sub N. Now, just as in flexural design, it is prudent to underestimate flexural strength, which is what we are doing by applying a phi factor smaller than 1. In shear design, the thing to do is to consider an overestimated flexural strength. Okay, but this overestimate has to be a reasonable overestimate. It is always easy to get carried away, but in the seismic design business, you have to resist the temptation to be carried away. So we take, in calculation of M sub PR, we take nominal member dimensions and the steel strength, if the stress in the tension reinforcement equal to 125% of the yield strength of the reinforcement. Remember, grade 60 steel can have actual yield strength up to 78 KSI, which is 1.3 times. So the 1.25 factor doesn't even take care of that entirely. And then steel can strain harden. Beams are under reinforced. The steel goes beyond yielding. So all of that will drive the number larger than 1.25, but 1.25 we have taken as a sensible number. If we cannot go for the highest that can develop, that will be getting carried away. That will make design very expensive without commensurate benefits. So nominal moment strength, design moment strength, probable moment strength. The hoops that I was talking about, this is a closed hoop, closed by a seismic hook. I have described the seismic hook already, 6 bar diameter extension subject to a minimum of 3 inches. Standard hook has a 6 bar diameter extension, a 90-degree bend, and no minimum. Okay. Now, instead of a closed hoop, which is difficult to fabricate and even more difficult to place, ACI 318 allows you these 2-part hoops, which stirrup with a seismic hook at each end, closed by a cross tie at the top. The cross tie has to have one seismic hook, one standard hook. And the seismic hook and the standard hook will be alternated end for end. On the next hoop, the seismic hook will go to the right face and the 90-degree bend will go to the left face, unless a slab is trimming into the beam on the right face, in which case all the 90 degrees will be on the confined right face, all the 135 will be on the confined on the unconfined left face. 318 goes into that level of detail when it comes to seismic detailing. Okay? And then you can have overlapping hoops as shown in the lower picture. Now from special moment frames, we go to intermediate moment frames. Special moment frames are the minimum requirement if your structure is in seismic design category D, which is pretty much all of the northern part of Dhaka. But if your design category is C, where the soils are good, let us say in the southern parts of Dhaka, you will require only intermediate detailing. Okay? So this is now the requirements for longitudinal reinforcement in intermediate moment frame beams. The two continuous bars top and bottom is no longer there. Instead of a maximum of 2.5%, the maximum now is the maximum for any non-seismic beam. We just say the net tensile strain shall not be any less than 0.004. I wouldn't go into explanation of that because I have a sense of time running. That is something basic that you should be able to remember or look up. The minimum reinforcement requirement remains the same as per special moment frame. Okay, same. But then, very importantly, at every support section, we shall provide at least 1/3 as much positive reinforcement as we have negative reinforcement. In a special moment frame, it was 1/2. In an intermediate moment frame, it is 1/3. 1/3 as much positive reinforcement as we have negative reinforcement. And then nowhere along the span of the beam can we have reinforcement less, can we have positive or negative moment strength any lower than 1/5 of the larger negative moment strength we supplied at the two support sections. In special moment frame, it was 1/4. Now it is 1/5 in the intermediate moment frame. Okay. So in the picture, we did not say two continuous bottom. But then if you look at the sections that I have cited here, it now says beams shall have at least two continuous bars at both top and bottom faces. Continuous bottom bars shall have area not less than 1/4 the maximum area of bottom bars along the span. These bars shall be anchored to develop F sub y in tension at the face of the support. Okay, I don't know that I need to explain any of this. So basically 1/4 of the bottom reinforcement, 1/4 of the bottom reinforcement at midspan has to continue into the supports. That's pretty much what we are saying. Transverse reinforcement, beams of intermediate moment frames. Same region of potential plastic hinging as for special moment frames. 2 times the total depth of the section. Within that, we now have to have hoops even in intermediate moment frames. There was a time we allowed stirrups, not anymore. The maximum spacing remains what it used to be for special moment frame, or in 31808 it is the same as the spacing requirement for special moment frames, except from 31811 onwards we have tightened the spacing for special moment frames but have not tightened it for intermediate moment frames. Are you with me? I hope I'm not confusing you. So in 31808, the spacing requirement for hoops in the plastic hinge region is the same for special moment frames and intermediate moment frames. That is your situation. Starting with 31811, in an important change, we tightened up on the spacing of transverse reinforcement in the plastic hinge regions of special moment frame beams. We did not do that for intermediate moment frame beams. So now there is a difference between the two. Okay. Outside of the potential plastic hinge region, we can have open stirrups at a spacing not to exceed 1/2 of the effective depth, and then where there are splices, we do not require, as we required in a special moment frame, that the splices be confined by closed hoops at a spacing not to exceed 1/4 of the effective depth or 4 inches, whichever is the smaller of the two. That requirement is not here. Okay. The shear design of intermediate moment frame beams. So we can do what we were doing. I don't remember if, yeah, I did throw in a picture. So there are two alternatives. One is similar to what we did for special moment frames. We consider the largest moment that can act at this support section, the largest bending moment that can act in the opposite direction of the other support section. We add the two together, divide by the clear span, then we superimpose the shear caused by gravity. Now, in the shear calculation for special moment frames, we used probable moment strength at each end of the beam. In shear calculation for intermediate moment frame beams, we use nominal moment strength acting at each end of the beam. That is the difference. Okay? Now, in the case of intermediate moment frame beams, we have another choice. The choice is described in words here, and I spelled it out more clearly on the next slide. So let us go through this. So the second alternative, instead of doing what we just talked about, considering nominal moment strength acting at the two ends, we can go with the shear obtained from structural analysis under code prescribed seismic forces, multiply that by 2 and add, so the shear caused by the design earthquake forces amplified by 2 shall be added to the shear caused by gravity. That is the idea. Okay. Snow you do not have in your case, so the last term doesn't count. The point is that we are taking the shear from analysis, amplifying that by 2, and then combining with shear caused by gravity loads. We do that for a beam of an intermediate moment frame. If it is a column of an intermediate moment frame, we have to amplify the shear from analysis by omega sub 0, which for an intermediate moment frame is 3. So 3 times the shear from analysis shall be combined with the shear due to gravity, and that will be our design shear. This is a second alternative that we have for intermediate moment frames, but not for special moment frames. Okay. I would say a topic. These are flat plate column frames that are allowed as part of as intermediate moment frames, but are not allowed to be special moment frames, as we discussed earlier. Okay? Now, when you have a flat plate as part of your seismic force resisting system, have a whole host of requirements that are quite important. So we are now going into those. Please follow me closely. And there are some problems that I will need to point out to you. Okay. So factor slab moment, including earthquake effects E, shall be determined for load combinations given in equations such and such. This is the additive seismic load combination. This is the counteractive seismic load. Reinforcement provided to resist M slab, that is the unbalanced moment, shall be placed within I think this page is probably because I have pictures that will explain it better. Let us start here rather than the other page. Okay, let's talk about the fundamentals first. So this is a strip of a flat plate that is continuous over supports. It could be a beam for the purposes of this picture doesn't matter. It could be a beam, could be a one-way slab, could be a strip of a flat plate. The blue curves show you bending moments caused by gravity. At the exterior support section, this beam support moment is an unbalanced moment that has to be transferred to the column. Entire moment is transferred to the unbalanced moment is the entire moment at the support section. By the time we are at the first interior support section, it is the difference between the bending moment of the column and the bending moment to the right of the column that has to be transferred to the column. So now the moment transfer, now the transfer moment is just the difference between the moments on the two faces of the column. By the time we arrive at the second interior column, there is no moment to be transferred. There is no, the bending moment to the left of the column is the same as the bending moment to the right of the column. There is no moment to be transferred. The joint is in equilibrium. Okay. Now that is the situation under gravity. The same beam or slab strip is now subjected to earthquake forces. We make our slab column frame or beam column frame part of the seismic force resisting system. The blue lines now show you the bending moments caused by earthquake forces. At the exterior support section, the entire moment is still the transfer moment, but the main thing is at the interior support sections, no matter where, it is the sum of the two moments to the left of the column and the right of the column. It is the sum of the moments that has to be transferred to the column. So the transfer moment is now considerably larger. I absolutely want you to appreciate this. This is the huge difference between a flat plate designed for gravity only and part of the resisting system. Whether you resist wind with flat plate column frames or moderate earthquake forces, design category C with flat plate column frames, you are looking at huge transfer moments at every support section. Now, okay, the reinforcement. Okay, what this says is, I'll skip it. I have in pictures what that says. Now, when there is a moment to be transferred from the slab to the column at a slab column joint, or beam to a column at a beam column joint, part of it is transferred by flexure, part of it is considered transferred by shear. The part that is considered transferred by flexure is gamma sub F times the transfer moment, and the part that is considered transferred by shear is the remainder. That's 1 minus gamma sub F times the transfer moment. This gamma sub F is 10% per square columns. If a column is rectangular, then the 60% will be somewhat different. And instead of a 60-40 split between flexure and shear, it will be 62-38, 63-37, something like that. It remains close to 60-40 even for rectangular columns, unless it's a pretty weird shape. Now, what do I want to say? So this is a plate running the direction of moment, left to right. Okay. If you take the central line of the bay, slab bay, let us say above the column, and the central line of the slab bay below the column, the central line to central line distance is the width of the design strip, width of the design strip. Out of that design strip, a part is designated as column strip, and the remainder are two half middle strips, as you all know, if you have designed a flat plate. Okay. So, first of all, the reinforcement that we need to resist the transfer moment, all that reinforcement must be placed within the column strip. And then the part of the transfer moment that has to be resisted by flexure, which is typically 60%, the reinforcement needed to resist that has to be placed within a narrow moment transfer band, the width of which is the transverse width of the column plus 1.5 times the thickness of the column on each side. So this narrow moment transfer band will have the width of C sub 2 plus 3H, with the stipulation that the 1.5 times the slab thickness cannot exceed the C sub T, which is the dimension from the inside face of the column to the edge of the slab if part of the column is sticking out of the slab. I think this picture is very graphic and totally understandable. So very importantly, the 60% of the transfer moment that must be transferred by flexure, the reinforcement required to resist that moment must be placed within this narrow moment transfer band. Okay, what we are doing is we are beams concealed within the thickness of the slab when your slab column frame is part of the seismic force resisting system. At an exterior column, the moment transfer band has a width of the column dimension plus 1.5 times the slab thickness, in this case on one side. Okay, the 1.5 times the slab thickness cannot exceed the C sub T distance that I indicated to you. Now within that narrow moment transfer band, this band from here to there, Okay, so let's start from here. All reinforcement necessary to resist the unbalanced moment to be placed in column strip, as I told you. So this is the slab strip from here to there. This is the column strip. This is a half middle strip. This is a half middle strip. And this is the narrow moment transfer band. All reinforcement necessary to resist the unbalanced moment, the transfer moment from the slab to the column, to be placed in the column strip. All the reinforcement has to be in that strip. Okay. Then reinforcement necessary to resist gamma sub F times the transfer moment has to be within that narrow moment transfer band, as I have been telling you, except that, not except that, in addition, at least 1/2 of the column strip reinforcement must be placed within that narrow moment transfer band. Okay. So if gamma sub F times the transfer moment is not very large, that will govern. Half the column strip reinforcement will be within the narrow moment transfer band. This is a very significant requirement. Okay. This is another picture telling you the same story. Here we don't talk about unbalanced moment, but the necessity to concentrate 1/2 of the column strip reinforcement within that narrow moment transfer band. There are additional detailing requirements. So this is the slab column frame. The upper picture is the column strip, the lower picture is the middle strip. Okay. As far as the top reinforcement goes, not less than 1/4 of the top reinforcement at the support must be continuous through the span. And as far as the bottom reinforcement is concerned, not less than 1/3 of the top reinforcement at the support must be continuous through the bottom of the beam. Please read this carefully. Okay. So not less than 1/4 of the top reinforcement at the support shall be continuous through the top. Not less than 1/3 of the top reinforcement at the support must be continuous through the bottom. All top and bottom reinforcement must be fully developed at the supports. And when it comes to the middle strip, the only requirement is not less than 1/2 of the bottom reinforcement at midspan shall be continued into the supports. Is the big problem area. When you design flat plates, flexure is not the problem. Our problem is punching shear. That's what causes failure of flat plates. But the loads are high and the spans are low. Slab column frames are susceptible to punching shear failures during earthquakes if the shear stresses due to gravity loads are high. Yeah. So this is very, very important. Punching shear is caused by gravity. There can be additional punching shear caused by earthquake forces. This is the moment transfer shear, if you like. So if gravity itself causes high punching shear, the chances of shear failure due to earthquakes is high. And that is a problem that we absolutely need to address. So ACI 318 has a very important requirement that says at the critical section for column, this is critical section for two-way shear that you are very likely familiar with. I have thrown in a few slides. We will go over that. So at the critical section for two-way shear, shear caused by gravity loads shall not exceed 40% of the shear that concrete alone can carry. V sub C is the punching shear capacity of concrete. 4 square root of F sub C prime in our units. Phi is 0.75. So 4 times 0.75 is 3 square root of F sub C prime. We are saying that the punching shear due to gravity shall not exceed 40% of that, and that will leave enough room for additional punching shear caused by earthquakes to be resisted by the slab without the help of any reinforcement. So this is a very important requirement of ACI 318 that, to my surprise, I did not find in BNBC. I checked with Dr. Rakib, and I can tell you that it is not there, and if it were there, it would have been in section 8.3.10.6. This is a pretty glaring omission, and all I can say is something needs to happen to reinstate it. I don't know what mechanism is available. Okay, now to say that shear due to gravity shall be lower than 40% phi times B sub C is easy, but in design that is a severe restriction. It will limit what we can do with flat plates, what spans we can use, what loads we can take. So very importantly, there is an exemption to this. You do not have to keep your gravity shear that low if you are able to satisfy a requirement that is provided in ACI 318. Okay? So now I threw in basic stuff here that now, in view of the time that is running, I am inclined to either skip or just point out the bare minimum. Okay, so the critical section for two-way shear is all around the column at a distance of 1/2 of the effective depth from the column face. Now, where in this case, there is what we call a drop panel. The slab is thickened locally at the column support. So where there is a column, the depth of the slab is the higher D sub 1. So the critical section is D sub 1/2 away from the face of the column. We consider a critical section around the column. We consider a second critical section around the slab thickening, and beyond the thickening, the slab has a thickness of D sub 2. So the second critical section is D sub 2/2 away from the face of the thickening. I hope you are following this. So in plan, the critical section for two-way shear looks as shown by the dotted lines in this picture: interior column, exterior columns, corner columns. You get the picture. And the total perimeter of the critical section is B sub 0 in ACI 318 as well as in BNBC 2020. Now, the punching shear carrying capacity of the concrete, V sub C, which I said is in our units 4 square root of F sub C prime. There are 3 expressions given. I wouldn't dwell on them. Everything is spelled out. This is the first expression. This is the second expression. And this is the third expression. 3 expressions given, and the smallest amount governs. And it typically comes, as I keep on saying, to 4 square root of F sub C prime in American units. And I do not know, the 4 is probably the, I don't know, 0.33 is the 4 square root of F sub C prime that I was talking about. So typically you will get that number or something a little bit different than that, but not very different than that. Okay. V sub C, the punching shear capacity of the concrete itself. Now, the exception. When can you not comply with the requirement that the gravity shear be kept below 40% of the shear that concrete alone can carry? Let me go to the bottom line. Okay, so if the shear due to gravity exceeds 40% of phi times v sub c, we have to provide some kind of shear reinforcement in the slab. Okay? And the shear reinforcement that was quite popular until let us say 10 years ago were stirrups like this in the slab. Okay? And you can read the words and things, it will make it clearer. But today, overwhelming majority of shear reinforcement is in the form of stud rails, as we call them. Thin metal strips with studs welded to them, and these studs have big heads. Compared to the standard Nelson stud, these heads are very big. So those heads anchor the legs, and when properly anchored, those legs resist the shear stresses, the punching shear. So those stud rails are now the shear reinforcement of choice in most applications. So in this picture, they have used, it seems to me, 3 stud rails in parallel at the slab column joint in both orthogonal directions. So those are post-tensioning tendons that are running, and this is the punching shear reinforcement at the slab column joint. This is a very, very typical situation. Now, let me again go to the bottom line. You can read this stuff. So let me explain this exemption from keeping the shear due to gravity very low. Now, in this picture on the x-axis, we have shear stress caused by gravity alone, V sub UG, divided by phi times V sub C. Okay. V sub C, you know, is the punching shear carrying capacity of the concrete itself. Phi is the strength reduction factor, which is 0.75. So if V sub UG over P times V sub C is 20%, that means the punching shear due to gravity is only 20% of what concrete alone can carry. That's very low gravity shear. On the y-axis is design story drift ratio. Design story drift is something defined in ACI 318. Story drift, first of all, is the deflection at the top of a story minus the deflection at the bottom of the same story. Design story drift is where the deflections that I just talked about are calculated under code prescribed seismic forces. So if you remember from my earthquake design courses, you take your design base shear, distribute it along the height of the structure in the manner prescribed by the code. That gives you F sub X forces at the various floor levels. You do a lateral analysis of the structure under those forces. That gives you delta, lowercase delta sub XE at floor level X. So that's elastically computed deflection at floor level X. To estimate design earthquake deflection, we amplify that by C sub D. So C sub D times delta sub XE at the top of a story minus C sub D times delta sub XE at the bottom of the same story is the design story drift. If you divide that by the height of your design story drift ratio, ACI 318 allows a design story drift ratio of no more than 2% for standard occupancy buildings, as you might recall. Okay, so now what we are saying is ACI 318 essentially says that you don't have to abide by the restriction on gravity shear, that it be kept below 40% of the shear that concrete alone can carry, if you would provide a prescribed amount of punching shear reinforcement at slab column joints that violate restrictions that we put into ACI 318. So what are those restrictions? That's what we are looking at now. So if the drip ratio is 0.005 or lower, 0.5% or lower, you are in this branch of the curve, and we are telling you that that the building is too stiff for anything to happen. Okay, and you need not worry about so until and unless the gravity shear exceeds 60% of the punching shear that concrete can carry, you do not have to provide any punching shear reinforcement. Okay, so if the drift is that low, below 0.005, then the gravity shear has to exceed 60% of the shear that concrete alone can carry for you to have to provide any punching shear reinforcement. On the other hand, if the gravity shear is only 20% of the shear that concrete alone can carry, then up to 2.5% reinforcement, there is no need to provide reinforcement. You will be fine without it. 2.5% will not even be allowed by ASC 705. If your gravity shear is 40% of the punching shear that concrete alone can carry, then we will allow you 1.5% interstory drift before you have to provide any punching shear reinforcement. So in other words, below this dark line, you do not have to provide any punching shear reinforcement even when your gravity shear exceeds 40% of the punching shear that concrete alone can carry. But above the line, on or above the line, you shall provide a prescribed amount of punching shear reinforcement. Okay? Then you have precluded punching shear failure of your slab. Okay? So this all important requirement is somehow missing from BNBC 2020. Okay, there is quite a bit, not quite a bit. There are a couple of things that I didn't quite tell you, but if you read the slides carefully and you have the slides, I think you will catch on. And time is tight. We lost quite a bit because of technical difficulties. So let me go on to now columns of special moment frames, members subject to bending and axial loads. So we are now talking about factored axial force exceeding 1/10 S sub G F sub C prime. Columns cannot be less than 12 inches in dimension. No column plan dimension can be less than 12 inches. In the US, I have never seen, never heard any complaint about it. But in foreign countries, I have noticed that this is a huge deal. You go to Bombay, they like 6-inch columns. Columns take up rentable space, and they would rather not have columns. If they have to have columns, they want them as small as possible. But if you look at the seismic safety of your structure, a column dimension less than 12 inches should not even be thought about. The long side to short side ratio shall not exceed 2.5. The long side of a column to the short side of a column ratio shall not exceed 2.5. If you have a member with long side to short side ratio exceeding 2.5, it doesn't mean you have to exclude it from your seismic force resisting system. All it means is that you cannot design it as a column anymore. It is now a wall, and you have to design it as such. Okay, so you don't have to throw it out of the seismic force resisting system, but it is not a column. That is important to realize. The detailing requirements and things change. Ever since the 1971 San Fernando earthquake, or the UBC edition that followed 1973 Uniform Building Code, we have the strong column weak beam requirement for special moment frames. The columns meeting at a joint must be stronger than the beams meeting at the same joint. The idea is, if and when we have inelastic deformations, which we allow, as I said at the beginning of the presentation, those better be confined to the beams and not spread to the columns, because beams are easily repairable, columns are not, and columns are also crucial to structural stability. So we recognize that in how should I say, if earthquake ground motion continues, eventually before failure of the structure, there will be plastic hinging at least at the basis of the columns, but to the extent possible, we want to confine the inelastic deformations to beams. So the specific requirement in ACI 318 and BNBC is that the combined flexural strengths of the columns meeting at a joint be at least 120% of the combined flexural strengths of the beams meeting at the same joint. Okay, so column strength at least 120% of the combined beam strength. This 120% many feel is not adequate, and as long as I have known things, there has been discussion of what that number should be, but 318 has stuck to 1.2, knowing that it does not prevent plasticity from spreading to the columns, particularly if earthquake ground motion continues. But this is a compromise between what is practical and what is what may be desirable. Okay, so I want you to understand that if it is a 3D joint, we are talking about 4 checks, 2 checks on the plane of the screen, 2 checks into and out of the screen. The sway from left to right is not the same as the sway from right to left. So those are 2 separate checks on the plane of the screen, and then into and out of the screen. For moments into the screen, it is 1 check. For moments away from the screen, it's another check. I'm sure you see what I mean. Okay, so 4 different checks for 3D joints. Now the moments that we are talking about, combined flexural strengths at column ends shall be at least 120% of the combined flexural strength of the beam ends. So moments that we are talking about are at the faces of the joint there was a time when we used to consider moments at the center line. It was very, very messy. So moments at faces of joint corresponding to the nominal flexural strengths of the columns and the girders. Okay, so nominal moment strengths. For columns, flexural strength shall be calculated for the factored axial force consistent with the direction of lateral forces resulting in the lowest flexural strength. This is very important. Strong column, weak beam. Okay, we want our columns to be stronger. So when we estimate the column flexural strength, we want to be on the low side. Okay, we want to underestimate, if anything, never overestimate. The beam strength, on the other hand, we want to overestimate. The overestimated, so the underestimated column strength shall still be at least 120% of overestimated beam strength. That would be a proper check. So in design, we have, remember, additive load combination and counteractive seismic load combination. Under additive load combination, M sub N2 is the nominal moment strength. Under the counteractive load combination, M sub N1 is the nominal moment strength. So when it comes to column moment strength, we will take M sub N1 rather than M sub N2. The beam moment, I said that we would rather overestimate it. So ACI 318 says consider the effective flange width, that is 12 of ACI 318 or 632 of BNBC 2020. All negative reinforcement within that effective width shall be considered as contributing to negative flexural strength of the beam. Okay, so that part of the beam will be considered as a flange of that part of the slab, rather, shall be considered to be a flange of the beam, and all negative reinforcement in that part of the slab shall be considered as contributing to the negative flexural strength of the beam. This is a specific requirement. Okay. Then we go to the longitudinal reinforcement in a column. Okay. There is other stuff in the figure, but well, only one thing I will not talk about transverse reinforcement here. So tension lap splice must be within the center half of the column height. That is a significant restriction. So normal practice is splices at the just on top of the slab. Okay, that is the easy location, and that's how it is done in non-seismic construction. But high seismic, when it is special moment frame, the splice has to be within the middle half of the column height. So that would require a crane hanging the cage, the upper cage, before, while those splices are installed. If you see what I mean. Okay. So the thing I want to discuss is the longitudinal reinforcement ratio, the gross ratio, steel area divided by concrete area, must be between 1% and 6%, minimum 1%, maximum 6%. The 6% in non-seismic construction is 8%. The 6, I would say, first thing is actually 3, because typically dowels will be coming out of the foundation, with which the column reinforcement will be lapped, and the lap splices count. So if you count the lap splices, your 6% goes down to 3%. I hope you are following me. This is deadly important. Next thing I will say is 3% reinforcement is a whole lot. If you don't believe me, draw 3% reinforcement to scale in a column section and you will see how much it is. After having placed 3% reinforcement in a column, it is not that easy to place the concrete and consolidate it properly. And one fundamental thing you always have to remember that fitting the reinforcement in does not do the job. Ultimately, reinforcement is good. It is absolutely necessary. Without it, there is no reinforced concrete. At the same time, reinforcement without concrete does not do you any good whatsoever. So ultimately, the reinforcement has to go in place and the reinforcement has to be properly consolidated. Okay? And all of that takes room. So you have to make sure that room is available. Anyway, so my advice to you, and this is probably the most important thing I will say all morning, our morning, your evening. Keep longitudinal reinforcement as low as you practically can. Minimum is 1%. You cannot always have 1%. I'm not suggesting that, but do not go high because just think of the beam column joint. The column reinforcement goes through, the column transverse reinforcement continues through the beam column joint. And then two sets of beam bars are passing, let us say from left to right, top and bottom beam bars. And then two more sets of beam bars, top and bottom, are going into that joint front to back. So the column longitudinal reinforcement continues, the column transverse reinforcement continues. There are top and bottom bars running from left to right. Those are the beam bars. And then there are top and bottom bars going from front to back. Those are the perpendicular beam bars. With all that reinforcement in the joint, you still have to have concrete go in and be consolidated. This can be a nightmare, and this is the make or break of concrete frame construction in high seismic areas. To make it work, you have to keep the longitudinal reinforcement low. The lower the number of longitudinal bars, the lower the number of cross ties and things that crowd up the joint, and the better off you are. So this it is I cannot emphasize it anymore how important it is to keep the longitudinal reinforcement low. The minimum 1% in non-seismic construction can be reduced to 0.5%. The ACI says if you have a larger column section than required by analysis, as you go up a building, the gravity loads go down. If you don't change your column section, your column has more area than required by analysis. Then you can decrease the reinforcement, but you cannot go below 0.5% of the actual column section that you have provided. Now, in high seismic construction, when a column is part of the seismic force resisting system, you cannot go below 1%. There is no 0.5% option. Transverse reinforcement, this is a circular column. I would not spend any time on it. Circular columns are very unusual in buildings. You find them in bridges, obviously, many times in parking structures, but other buildings no. And I do not know exactly why. I suspect it is because beams are always rectangular And if the column is circular, the beam column joint becomes very difficult or messy to detail. I think that is the reason that we do not use them in buildings, not much anyway. So for spiral reinforcement in a column, which would be typically a circular column, there is a clear spacing requirement of the pitch of the spiral, and there is a minimum volumetric ratio requirement, and that's all I'm going to say. All around the world, you will see columns that have plenty of longitudinal steel. If they're spirally reinforced, the spiral reinforcement is not sufficient, low ratio of spiral reinforcement. This is a column after the 1985 Mexico City earthquake. You see what has happened to it because of the lack of confinement. The same story. This one has crashed at the bottom. This one has not quite done that, but this is not a redeemable situation. This column has to be replaced. So I showed you this picture before. Now I will discuss details that I didn't discuss the last time. So this is a column of a special moment frame. We have a region of potential plastic hinging at each end, within which we have to have closely spaced closed hoops. The hoop spacing shall not exceed any of the three. Okay. And more importantly, the legs of the hoops must have an area no less than the larger amount given by the two formulas. And I pointed out that when you have high strength concrete, this poses a problem. Okay. Now, this requirement I did not dwell with the last time. Outside of the potential plastic hinge region, the spacing of column ties, outside of that region, you can use ties. You don't have to have hoops. Ties can be closed by 90-degree hooks, and you don't have those onerous cross tie requirements. Now the maximum spacing of 6 inches and or 6 longitudinal bar diameter, whichever is less, was added after the Northridge earthquake of 1994 because many columns failed by shear cracks developing where we left off the special transverse reinforcement, the closely spaced transverse reinforcement. This spacing used to be 12 or 14 inches as permitted for non-seismic columns. Now it is 6 inches or 6 longitudinal bar diameter, whichever is the smaller of the two. This has been a major change, post-Northridge change, that I suspect has done us a lot of good and will continue to do us a lot of good. So in a special moment frame column, you cannot have a spacing larger than or 6 inches, whichever is the smaller of the two, anywhere along the height of the column. Okay. The confinement that I already talked about, so every other bar laterally supported by a corner of a tie or a cross tie, maximum spacing center to center between any two supported bars 14 inches. The maximum clear spacing between a supported bar and an unsupported bar 6 inches. Okay. And you see the hooks arranged the right way. The only thing S sub x, this I did not explain to you. S sub x is between 4 and 6 inches, first of all, 100 to 150 millimeter. S sub x depends on the idea behind S sub x is if we have, so it's a matter, what confines the concrete is the column cage, is the longitudinal plus the transverse reinforcement forming a cage. So if the spacing between the horizontal legs is close, if the horizontal legs are close together, then we can go easy on the vertical spacing of the transverse reinforcement. On the other hand, if the horizontal legs are far apart, then we have to tighten up on the spacing, on the vertical spacing of the transverse reinforcement. Okay. So these x sub I values, you see what they are. The largest value of x sub I around the perimeter is called h sub x. And the s sub x is 100 plus 350 minus h sub x, the whole thing divided by 3. And as I said, it is between 6 inches and 4 inches. So this is your expression for s sub x. The larger the h sub x is, the spacing of the horizontal legs, the larger the s sub x, and the smaller that value is, the smaller s sub x. Okay. So this is the idea of the column cage. Now, shear design of columns. What this is saying is, okay, the first part is very easy to understand. So in the shear design of a column, the simplest thing to do will be to take the probable moment strength acting, let us take the lowest column. Take the probable moment strength acting at the base of the column. Let us say it is counterclockwise. You take the probable flexural strength, again counterclockwise, at the top of the column. You add the two together, divide by the column height, that is the column shear. If you take clockwise moments at the two ends, you will get the largest shear in the opposite direction. So the first thing we say is that you take M sub PR at each end and calculate shear on that basis. But then the point is, because of strong column weak beam requirement, probable moment strength of the column cannot develop except at the base of the column. At all other joints, the largest bending moment that can develop at a column end is the largest bending moment that the beams framing into the joint will bring onto the column. And that is the subject of this picture. So this is a column above the joint. This is the column below the joint. This is the beam to the right of the joint. This is the beam to the left of the joint. This is the joint. Okay. So the beam to the left is under negative moment we are considering. So the largest bending moment that can develop in that beam section is M sub PR. We added L for the negative moment. Okay. At the other beam is then has to be subject to negative moment. So the probable moment strength is now M sub PR, R for the right beam, and negative for negative bending moment. Now this M sub PR L positive plus M sub PR R negative, the sum of the two has to be balanced by column moments. So if the column above and the column below are identical, then the sum of these probable moment strengths will be divided half and half between the lower column and the upper column. So M column will be M sub PR L plus M sub PR R divided by 2. Okay. Now the largest moment that can develop in the lower column, upper end of the lower column or the lower end of the upper column, is this moment that we just talked about. And that would be lower than the probable moment strength because of strong column weak beam requirement. So when we calculate column shear, we consider probable moment strength at the very base of the lowest level column, but at all other column ends, we go by the largest bending moment that the beams framing into the joint can induce at the column end. I hope that is clear. I think the picture should be clear, and so let's go forward. So this short column failure, this is something we see after every earthquake everywhere. What is happening here is engineer has designed based on a column height from the top side of the lower floor to the bottom side of the upper floor. But then somebody decided to build this parapet which has cut down on the column height. And the shear induced in the column is the sum of the bending moments at the ends of the clear column height divided by the clear column height. Okay, so the shear was calculated based on an 8-foot column height. The 8 foot has been reduced to 5 feet because of the parapet, and now we are talking about a hugely increased shear in this column. The shear capacity has not been increased, so what happens is the shear failure of the kind that you are looking at. Very column. This is called short column effect. This building we looked at after the Northridge earthquake of 1994, every joint had this because the shear was calculated from central line of beam to central line of beam above, and then the height of the column or the short height, that meant hugely increased shears that caused diagonal shear cracks in both directions. Okay, next topic is column supporting discontinued shear walls. I have shown you this picture probably more than once over the number of days we have been talking to one another. So this column, that column, that column, that column are supporting discontinued shear walls. Okay, for those, so in a column, normal column of a special moment frame, you have seen that we provide closely spaced closed hoops within the potential plastic hinge region at each end of the beam. If it is a column supporting a discontinued stiff element, then the closely spaced closed hoops that we would have placed only in the plastic hinge region has to be provided throughout the height of the column and then into the foundation for at least 300 millimeters. And at the upper end, the transverse reinforcement shall continue for one development length of the largest longitudinal column bar. Okay, so the special transverse reinforcement, as we used to call it in 31808, it is still called that. The special transverse reinforcement, the closely spaced closed hoops in the plastic hinge region, has to be provided throughout the height of the beam of the column supporting a discontinued shear wall, at least 12 inches into the foundation, and at least the development length of the largest longitudinal column bar into the discontinued shear wall. Okay, now we come to columns of intermediate moment frames. If a column of an intermediate moment frame or a column with intermediate detailing, let us say, is supporting a discontinued shear wall, then what we do is the same. Whatever we would have provided in the plastic hinge region is provided throughout the height. but now instead of 4-inch spacing, because the spacing is relaxed, okay, as you will see. So this is a column of an intermediate moment frame. What are the transverse reinforcement requirements? Yeah, this sign was wrong in, remember way back I was confused. Let me check. It will take only a second. There are things I do not notice for some reason until I start presenting. Yeah, this sign is wrong. This is larger than or equal to. It's the largest of the three that gives you the plastic hinge length. Okay, so this is what confused me at the beginning of the presentation. So please change that sign. This picture you have at the front. So this should be larger than or equal to, as I have in the intermediate moment frame picture. Okay, so the plastic hinge length is the same. It's the larger plane dimension, 1/6 of the clear span, or 450 millimeter, whichever is the largest of the three. Within that, we have to have closely spaced closed hooks these days. No ties. Okay, the spacing is the smallest of those four. 8 longitudinal bar diameter, 24 hook diameter, etc. So huge. This is a big difference between a special moment frame and an intermediate moment frame. In a special moment frame, that spacing would be 4 inches or typically less because of the cross-sectional area requirement. In an intermediate moment frame, this spacing will be 8 or 9 inches typically. Okay, and very importantly, there is no minimum cross-sectional area requirement. This is a huge difference between an intermediate moment frame column and a special moment frame column. No minimum cross-sectional area requirement. Outside of the region of potential plastic hinging, we no longer say 6 times the bar diameter or 6 inches, whichever is less. We say whatever you do for non-seismic columns by Chapter 7 of ACI 318 or the shear reinforcement requirement of Chapter 11 of ACI 318. So this is now the non-seismic detailing that takes over outside of the region of potential plastic hinging. Okay, beam column joints. Maria is pointing out, I see we started at 7:30, so we should have ended by now. Let me continue because we lost quite a bit of time today, and if you have to go, you have to go. I'm sorry, but I don't want to. The other choice is I can add this to tomorrow's presentation, but then let me see how much. Let me finish this up. As I said, if you have to go, please go. You have the slides, and I'm sure you can catch up. Let me finish this up. It will be what's the time? 11:30 hour. 11 whatever. I don't know. It will be 10:30 your time, I think. Okay, let me, you have to go, Maria? No, okay. Okay, so this is an exterior beam column joint. The top beam bar as well as the bottom beam bar are ending at the joint, and they have to be fully developed at the face of the joint. If this were a non-seismic beam, the hooked bar development length would have come of ACI 318. But ACI 318.08 section 21.7 modifies what chapter 12 tells us. The hooked bar development length is modified to what you see in this expression. And the commentary says this is about 40% larger than what chapter 12 would have required, because these bars are subject to stress reversal in an earthquake. Okay. So that is something important. This is an important case of something in the front part of the code being modified by 318 chapter 21. Also, it goes on to say if you have straight beam bars terminating at the joint, the required development length shall be 2.5 times the hooked bar development length if it is an other than top bar, and the required development length shall be 3.5 times the hooked bar development length if it is a top bar. A top bar is defined as a bar having more than 12 inches of concrete cast in one lift underneath the bar. Again, a top bar having more than 12 inches of concrete cast in one lift underneath the bar. So, when a beam bar simply passes through a beam column joint, an interior beam column joint, I don't know if you have ever thought about this. This top bar on the right side of the column, right face of the column, is in tension. It's negative bending moment. On the left face of the column, short distance away, the bar is in compression. It is positive bending moment. So the stress in the bar changes from tension to compression within the narrow confine of the column width. And that change takes place through bond with the concrete. So there is every considerable bond slip within the joint, which will increase the lateral displacement that the frame will suffer in an earthquake. So we want to minimize this bond slip. And in order to do that, ACI 318 has prescribed minimum column dimensions. The column width has to be no less than 20 times the largest longitudinal bar diameter. Okay. Now, when you see, when your column dimension does not satisfy that requirement, I have never seen somebody going for a larger column. You typically go for smaller column bars because remember, larger column means more rentable space taken up by the structural element. So you go for thinner column bars and then it works out. Now, joint shear, how much shear a joint can carry. To calculate that, you need effective area within the joint, the shear stress capacity, you will see. So what is the effective area within the joint? When the beam framing into the column is as wide as the column or wider, the effective joint width is the column width. Very simple, okay? If the beam is as wide as the column or wider, the effective joint width is the column width. But when the beam framing in is narrower than the column, the effective joint width is the smaller of two things, either the beam width plus joint depth as shown in the picture, or the beam width plus twice the shorter distance between the beam face and the column face. So whichever is the shorter of the two, and typically this is the shorter of the two. The beam face plus twice the shortest distance between the column face, the beam face and the column face. This distance is shorter than the distance the other way. Okay. Now, when we say shear at a joint, what is the shear at a joint? I was thinking of something, whether I want to go there is what I'm, let's not go there. Okay, so this is the beam column joint. Shear here at section XX, let us say, is the sum of the tension in the top reinforcement of the right beam, the compression in the top, the compression in the top concrete in the left beam, plus the compression in the top reinforcement of the left beam. This is now compression reinforcement, compression concrete. So the shear here is tension plus that compression plus all the concrete compression minus the column shear. What is the column shear? We go back to the picture that I already showed you. This is above, the column below. This is the joint. We know where this column moment comes from. This is half of the sum of the probable flexural strengths of the beams. You have a column moment at the bottom end of the column. You have a column moment at the top end of the column, which comes from the upper joint. You add the two column moments together, divide by the height of the column. That gives you column shear. Okay, equal and opposite shear acts on the joint. So the shear at the joint is this tension plus all this compression minus the column shear. How much shear can a joint carry? If it is a joint confined on four faces, it is 20 square root of f sub c prime times the effective area within the joint that we just talked about a short time ago. Okay, 20 in our units. If it is a joint confined on three faces or two opposite faces, it is 15 square root in our units. And for corner joints, no confinement, it's 12 square root of f sub c prime in American units. Okay. Now, what is a confined joint? A confined joint has beams framing into all four faces, with each beam wide enough to cover 3/4 of the column face. This is what the verbiage on the slide tells you. So a confined face is a face that has a beam framing in with the beam width covering 3/4 of the column width. Okay. So confined face is defined. Four faces confined, you get 20 square root of f sub c prime times sub j. If the joint exceeds the shear carrying capacity of the joint, the 20 square root of f sub c prime multiplied by a phi factor, which for a joint, I think we still allow 0.85, whatever the phi factor is, then you have to do something. The alternatives open to you is you can go for higher concrete strength that would boost shear capacity, but it is square root of f sub c prime. Remember that shear strength is proportional to, so that makes it ineffective. You increase concrete strength 4 times, 4 to 16 ksi. you get only a shear strength increase by a factor of 2. Or you can go for a larger joint, A sub j, increase A sub j by increasing column size. That is also something the owner wouldn't like. So your choice really is, effective choice is to go for deeper beams, because when you have deeper beams, this tension and that compression decreases. And so you will be dumping less shear onto the joint, and that would then solve your problem. That is what we always do. Okay, these are some instances of so as I mentioned, the typical joint has the column cage going through. It's the column reinforcement going through the joint. More importantly, all the column transverse reinforcement going through the joint. And then the beam bars must pass through the column cage, not outside. Here, the beam bars are not confined by the column cage. And you see that the joint has not done well. This was a Kaiser Permanente facility after Northridge, and this was I think it is my own picture. Look at this here. Those were beams of two different floors. This is the beam of the lower floor. This was the beam of the upper floor. This floor has pancaked, as we call it, because the column separating those two beams is hanging out here. And that happened because these are pre-1973 joints which did not have any transverse reinforcement pretty much. Okay, so this joint reinforcement is quite important. Now, when we go to joints of intermediate moment frames, we do not have too many requirements. It's basically, and I wouldn't bother you with the slides. It's basically you have to provide the shear reinforcement required by the code, and you have to, and when the shear is low, you have to provide the minimum shear reinforcement required by the code through your intermediate beam column joint. That's all that 31808 ever told you. That has now changed pretty drastically in later editions, but I wouldn't bother you with that. Okay, to end the seminar, I want to say two things. One is that NIST, National Institute of Standards and Technology, publishes these so-called tech briefs, TECH BRIEF, on technical topic, on structural engineering topics. These are publications of just about 40 pages that are for the practitioner. These publications are every one of them is excellent, and you can get them free of charge on the internet. Just Google NIST Tech Brief. By now there are 13 or 14 of them. This is the first one, Tech Brief number 1, Seismic Design of Reinforced Concrete Special Moment Frames. I think that it will be worth your while to get hold of a copy. And finally, I want to make a point which I think is to me very significant. So this is my last slide today. Okay, and by now you know that there will be no questions, which is regrettable, but that's the timing is working out. And we will see what to do with the questions. I still don't know. This is this frame was part of a parking structure on the campus of Cal State Northridge, California State University Northridge, not very far from the epicenter of the 1994 Northridge earthquake. The building has failed because the gravity columns inside the building failed. So, but the building has fallen inwards. I want you to see that. You know, the frame has not fallen out, which could have happened. Now, this frame, first of all, when we detail a special moment frame with all the care and following all the requirements we went over, what we are trying to do is to give it inelastic deformability, deformation capacity in its own plane. We want the frame to be able to deform in its own plane by a significant amount without losing gravity load carrying capacity. Here, the special moment frame on the periphery of this parking structure has undergone out of plane displacement of something like 5 or 6 feet. And these columns are surprisingly intact. They're not undamaged. There was cracking, but no pieces have flown. The column has not crushed. It's to me, this is remarkable performance. Okay, so the special detailing, it is onerous. The requirements are onerous. The checking is not easy. Nothing is easy. But you see that the performance improves. This is what we have learned through experience through many earthquakes, the requirements that you are seeing in SCI 318 today. So I would strongly urge that you follow, first of all, you understand the requirements, then you follow the requirements when you design, and inspectors and people who check these things be meticulous about their checks. Okay, thank you very much. I really am sorry I kept you with a half hour beyond your beyond the scheduled closing time, and even then I cannot take questions. But anyway, tomorrow hopefully it will be shorter. Hopefully we will not have technical difficulties. We will do before we start whatever solved our problem today. And with that, please have a nice night. I will see you again tomorrow night your time. Shear wall detailing. Thank you very much.